Hello engineers, welcome to the new video of the course, and in this particular video we are going to simulate the inverting amplifier circuit based upon Opamp onto the LTSpice software. Okay, so for that let me just open a new schematic and then we will design the circuit, that is our inverting amplifier. So first thing first, we need to take the voltage source, and since we are dealing with dual supply, we need a dual supply. So over here as well I'll just take two voltage source to give a dual supply to the to our op-amp, right? And then obviously we need one operational amplifier. So for that, you see over here I'll just click on component, and then I'll just go in op-amp, and instead of searching I'll just type LM741. So you see we have one op-amp, that is LM741. So I'll just click on OK. I'll just put it somewhere over here. Okay, and then I'll just click on escape button, and then I need 2-3 grounds over here, 2, and I'll put 1 ground over here. Okay, and then obviously now this time I just need to connect one resistor, right? So if you can recall the circuit which we had seen in our previous session, so you see this is how the circuit looks like. So we have one feedback resistor which is connected in between the output and the input terminal. Obviously we will be connecting it to the negative terminal, since for an amplifier we want a negative feedback, right? We cannot give a positive feedback if we want to operate our op-amp, or in general any device like BJTs and FETs to work as an amplifier, right? If we are going to connect it to positive, so it will act in the saturation mode, and we really don't want this to happen, right? So you see the connection how I had connected over here. Okay, but now before designing this particular circuit, what we really need to understand is that what should be our gain. Okay, so we'll try to keep the things as simple as possible. So for that very purpose, what I really want is that my gain, like whatever the circuit that I'm designing with the help of inverting amplifier, it should be able to provide a gain of 2. Okay, it should be able to provide a gain of 2. I know 2 is a very small number, but still this is just for experimenting purpose. So we'll try to keep the things as simple as possible. So we'll try to make our gain as 2. Okay, 2. What does that mean? If that means if my input voltage, if my V in is of 1 volt, okay, 1 volt peak, okay, so my V out will be 2 volts peak. Okay, that means peak to peak amplitude will be 2 volts. That means if my V in, let me write it in this way, if my V in is 1 volt peak or 2 volts peak to peak, okay, 2 volts peak to peak, so my V out will be, this time my V out will be 2 times of Vp, or 4 volts peak to peak, 4 volts peak to peak. Okay, this is what we want. Okay, so now that we are quite familiar with the gain, okay, so we can easily design this particular circuit. So for that very purpose, we need to just recall the formula which we saw, and we saw that the gain for inverting amplifier is nothing but RF by R1. Okay, this negative sign indicate that my output signal will be 180 degree out of phase, right? So this is what it means. So we don't need to focus upon the negative sign, rather our point of interest should be the resistors that we are going to connect. So the resistor RF should be 2, okay, 2 times of the R1. Okay, so what does that means? My resistor RF, okay, my resistor RF should be 2 times of R1. So if my R1 is 1 ohm, so RF should be 2 ohms. If my R1 is 1 kilo ohm, my RF should be 2 kilo ohms. I hope you are able to understand this particular point. Okay, so what I'll do, I'll just erase this particular part over here, and I'll just write it somewhere over here, so that whenever you will refer my PDF, it will be pretty easier for you to understand this entire things. Okay, so that is, I'll write it in this way, that is my RF should be 2 times of R1. So whatever the value of R1 will be, my RF should be 2 times of that resistor R1. Getting my point? So let me just highlight it, because this is the point of our interest. This is the major part for designing an inverting amplifier. Now let me move back to the circuit. So now that we are quite familiar with the values of the resistor, so I'll just select the resistor, Control R to rotate it. I'll just paste one resistor over here, somewhere over here, yeah, and I'll just zoom out this particular circuit. Okay, great. Now let me just drag all of the components so that it will look neater. Yeah, somewhere over here, ground. Let me move it little down. Let me arrange this entire things. R2, I'll just make sure that I'll connect somewhere over here, R1 somewhere over here, V somewhere over here, and this V somewhere over here. Okay, great. So now I just need to connect the components, connect this particular components with the help of wire. So as I said, just need to go through the entire component so that the software actually automatically it detects the endpoints, right? This will be connected to ground. Great. And then yeah, the positive supply will be connected to the plus VCC, and this will be my negative terminal. It will be connected to minus VCC. Okay, great. And this will be my output terminal, which I'll connect in this way. So this is my feedback resistor, and I'll connect somewhere over here. Okay, and then this ground will be connected in between these two DC supplies. Okay, I hope you all guys can remember the concept of dual supply mode. I had already explained that, right? Now we just need to feed the values for the voltages and the resistors that are available. So RF is, as I mentioned, it should be 2 times of R1. So as of now I'll consider it to be 2K, and when I consider RF as 2K, so my R1 should be 1K. Okay, it is as simple as that. And then we need to focus upon V. Okay, so we need to provide a sinusoidal waveform, or rather AC signal. So what I'll do, I'll just right click over here, and we really don't want DC value over here. So for that I'll just click on add once. Okay, and I'll just click on sine, and DC offset I want 0. I don't want any offset voltage. I want amplitude as 1 volt peak. Okay, so whenever you will enter amplitude over here, that is 1, so it will take a peak value, not peak to peak value. Okay, getting my point? And then frequency, you can enter any frequency. As of now I'll just consider as around maybe 1 kilohertz. Okay, we'll go with 1 kilohertz. I'll click on OK. Great. And yeah, we need to supply certain DC voltage as well. So for time being I'll consider it as 15. Okay, 15. You can take 10 volts and 12 volts as well. It's up to you, but don't go below 3 volts or 4 volts or 5 volts. That is not a good idea, because our input signal is of 1 volt, so it can clip that particular above part or the lower part. So it's advisable to stick around 7, 9 or voltages above 10 volts. That will be a good idea for this particular purpose. I'll come to this particular part, that what value we really need to select for this particular voltages. Okay, as of now don't worry about that, just do as I'm explaining. Okay, let me just connect one wire over here. Yep. And now we need to just label this particular input and output. So for that, as I had mentioned, that we just need to right click over here, label net, and I will type V in, that is my input voltage. I'll click on OK. I'll paste it over here, and same thing over here for V out. I'll just right click on it, label net, V out. Okay, and I'll just put OK over here. Great. Let me put escape button, and let me press escape button, and then we need to just run it. And once if you run it, it will ask for the transient analysis to see that particular waveform. So my stop time should be of 10 milliseconds. My start time should be 0 millisecond. It should actually start from 0 millisecond, and maximum time step should be 1 millisecond. So let me just write 10 millisecond. Okay, great. And you see this kind of window will appear. Great. Now we just need to put our input and output waveform. Okay, so before showing the input waveform, let me just show it to you over here. When I said that my input waveform is of 1 volt peak, so what does that mean? I'll just draw it for you all guys roughly, so that it will be pretty easier for you all guys to understand this particular concept properly. So you see, this will be my input waveform. I know my drawing is not that good. Okay, something like this. So let's assume this is my input waveform. Okay, something like this. Getting my point? Let me draw it properly. Yeah, you see, so this particular voltage from here to here, it is of 1 volt. Okay, 1 volt, 1 volt Vp, 1 volt. Okay, and obviously when I go down, so it will be minus of 1 volt, sorry, yeah, when I go down, it will be minus of 1p, right, minus of 1 Vp. So you see the overall amplitude, it will be 1 minus of minus 1, so this will be 2 volts peak to peak. So this is what I explained over here. So I'm providing input voltage of 2 volts peak to peak. Getting my point? Great. So now what we'll do, we'll plot the input waveform over here. So for that, yeah, I just need to go near to this particular pin and I just need to click over here, and you see one input signal is occurring. You see over here it is moving from 0 volts to 1 volts. Let me just zoom it out for you all guys. Yeah, you see, let me move it over here. Yeah, you see it is starting from 0 volts, moving above at 1 volts and moving below at minus 1 volts, and this is what I had drawn over here. You see 1 volts above. Let me just show it to you over here once again, so that there shouldn't be any scope of confusion. Okay, so plus 1 volts, and over here this is my minus 1 volt. Okay, great. And this is what we can see over here. Okay, getting my point? Great. Now let me just select this particular option, that is tile windows, and yeah, you see again we are back to this particular step. Now I just want to see my output waveform with respect to the input waveform. So what I'll do, again, just click over here and then I'll just click on this particular wire, and you see we are also getting one output waveform, and I believe that this particular waveform is visible to you. If you want, you can change the color. Okay, I'll make it as pink. Okay, so you see this is my output waveform. Let me just zoom it out for you all guys. Okay, but before coming to this particular part, as I had mentioned that, you know, this is my inverting amplifier, right? Okay, so when I say that this is my inverting amplifier, so I should get this kind of output, so something like this. So you see, I'll recommend you to please take a screenshot of it. I believe that you have taken a screenshot of this particular image. So now I'll just erase everything because it is looking little messy. So I'll just erase all of the things. It's not required as of now. Yeah, it's fine if we keep this, but let me erase this as well for time being, and let me move it to the right side. Okay, that's fine. Great. So now let me just draw the output waveform. So this should be my output waveform. Again, I'm drawing it a little roughly so that it will be pretty easier for you all guys to understand the concept properly. So you see over here, this time over here the output waveform is of plus 2 volts and this is minus 2 volts, right? So over here, let me just write it properly. Yeah, so my input signal was of it was moving from plus 1 volt to minus 1 volt, right? And my output signal, it is moving from minus 2 volts to plus 2 volts, right? Getting my point? So you see my output waveform, it is 2 times of input, right? So this is what I had written over here. My input is 2 volts peak to peak and my output is 4 volts peak to peak. Okay, and this is what, if you look over here, this is what we are getting over onto this particular screen, right? So you see my V out, as you can look over here very clearly, it is moving from minus 2 volts. I don't know if this is visible to you all guys or not, but for you all guys I'll just mark it. So you see this is minus 2 volts and this is plus 2 volts, right? So this is plus 2 volts and this is minus 2 volts. Okay, for a time frame of 10 millisecond, which we had already selected, right? Getting my point? So this was all about you know, the inverting amplifier. This is how we exactly perform the operation for the inverting amplifier, and you can clearly look over here, we're exactly getting the waveform, inverted waveform, and that is amplified by 2 times of the input signal. Getting my point? So let me just click on this option, tile windows. Okay, great. Now we need to see the frequency response of this particular amplifier. Okay, why? Because if you could remember, I had clearly mentioned that. Let me check if I had kept that particular or not. Yeah, I had clearly mentioned that my frequency response of the op-amp, it is around 1 to 20 megahertz. Okay, it depends upon the op-amp that you are using, but it should be above 100 kilohertz for certain application. Okay, as such, the circuit which we had designed, it is I mean, it can be used as in various applications, but this is a very normal circuit. We had not connected any compensating resistor over here, and obviously we need to do certain variations in the circuit to get the desired gain, or to get the appropriate gain for higher frequencies. Okay, but we had not done anything into this particular circuit, but still we just need to check that what would be our frequency response. Okay, so for that very purpose, as I had already mentioned that like we actually get a kind of privilege onto the LTSpice software to check everything. Okay, within a window, right? We can create various windows or various screens, and we can analyze lots of things over there. So what I will do, I'll just click on new schematic. As you can see, a new window is appearing, so I'll just move it somewhere over here, and then I just need to copy this particular circuit onto that particular window, right? So I'll just select the entire circuit, and then I'll just put it somewhere over here. Okay, and then what I need to do is I just need to click on this option, simulate, and then edit simulation, and then I just need to do AC analysis. I'll just take a decade, since we need to see the frequency response, right? And then points per decade, I'll consider it as 100, and frequency I'll start from 10 hertz. Okay, sorry, yeah, this is start and stop should be of 10 megahertz. 10 meg, just write 10 meg. I'll click on OK. I'll just put it somewhere over here, and I will also need to change this to none, and I just need to keep AC amplitude as 1, since we are providing 1 volt, right? So I had kept it as 1, right? And then we just need to run this particular circuit. Okay, and then we want frequency response at the output side, so we will just click. See, you see a probe like symbol is appearing, so we will just click on the output side, and you see we are able to get the frequency response of this particular circuit. Okay, but what we really need to understand is that how exactly it is behaving. So you see, forget about what gain we are getting, you just see the frequency response. As of now, we just need to understand if the frequency response, so whether we are able to get a stable gain at higher frequencies or not. That is the point of our interest. Okay, so you see, at this particular frequency, like we don't know what that particular frequency is. Okay, but you see above 100 kilohertz as well, above 100 kilohertz, you see, I don't know if it is visible to you guys or not. I'll zoom this particular image or this particular screen for you guys, but as of now, just try to see over here. So you see, this is 100 kilohertz. Somewhere over here, this is my 100 kilohertz, and above 100 kilohertz as well, till this particular point, maybe till this particular point, we are able to get a stable gain, right? So up till this particular point, we are able to get a stable gain. Stable gain. That means what? It is I mean, my circuit is actually providing a gain of 2. Okay, my circuit is actually providing a gain of 2, so my V out is almost 2 times of V in. Okay, but after this particular point, my gain is actually decreasing, right? My gain is actually decreasing, but you can clearly look over here, it might be around 0.5 megahertz or maybe 500 kilohertz. We don't know that. Okay, we don't know that, but what we can see is that at higher frequencies as well, we are getting a stable gain, and this is what we wanted. If you try to recall the characteristic of op-amp, right? If you try to recall the characteristic of op-amp, so over there we had studied the this particular entire characteristic, right? We actually saw this characteristic, and I had clearly mentioned over there that the bandwidth for an ideal op-amp should be infinite, but that was for an ideal op-amp, right? But for practical op-amp, it should be as high as possible. It depends upon the operational amplifier that you are using. Okay, for IC741, it is around 1 megahertz. Let's check that. We'll type on Google as well, and then we'll see the data sheet as well, right? So bandwidth for IC741 Opamp, IC741 Opamp. Yeah, it's around 1 megahertz. Again, this is some random block, so we don't need to refer that. We will see the data sheet. So data sheet of IC741. Just type on Google and let's check that what value we get, right? So let's check where we get that particular value for bandwidth. Let me check if it is available over here. No, bandwidth is not present. Over here as well, bandwidth is not present. Yeah, you just have a look over here. I don't know what is this page number. Yeah, at page number 6. And by the way, this data sheet is of Texas Instrument, I believe. Yeah, TI stands for Texas Instrument. So let me just zoom this particular entire thing and let me move it somewhere over here. Where it is. Yeah, you see bandwidth. Okay, TA 25 degrees Celsius. But before that, I just forget to check if it is, if it is data sheet of 741 or not. You can clearly look over here. This is the data sheet of IC741, that is the operational amplifier. And now let me go down once again, and you just check the bandwidth where it is. Yeah, you see the bandwidth at 25 degrees Celsius. The bandwidth will be around 0.4 megahertz to 1.5 megahertz. So we should always consider the typical value. It is 1.5 megahertz, right? So our op-amp can withstand this particular frequency as well, that is 1.5 megahertz. Okay, so you see over here on an LTSpice, okay, although we are not getting a stable frequency up till 1.5 megahertz, but still we are able to get a stable gain above 100 kilohertz. Okay, that means around 0.1 megahertz. Okay, obviously we need to do certain modifications in this particular circuit to get a stable gain up till 1 megahertz or something like that. But still, what was my point to show this particular frequency response? My point was that, see, my op-amp is able to provide a stable gain at higher frequencies as well. So what does that mean? So as I had mentioned that, whenever we are designing any amplifier or any system, we want that it should be usable for all the engineers out there. So since I'm a biomedical engineer, right, so I'll be taking certain signals from my brain or from my heart, right? So the frequency of those signals will be of around 10 hertz, maybe 70 hertz, maybe 50 hertz. Okay, so my op-amp should be able to amplify those signal as well, whose frequency is around 10 hertz, 25 hertz, 70 hertz, 60 hertz, right? Now let's suppose if someone is from telecommunication background, okay, so he might play with some radio signals, whose frequency will be around 100 kilohertz, maybe 200 kilohertz. Okay, we don't know what that particular frequency is, but the frequency will be quite high, right? And if he or she wants to amplify that particular signal, so our op-amp should be able to do so, right? So that's why op-amp is a device, or rather op-amp is created in such a way that it can actually withstand all of the frequencies. Okay, not all of them, but most of the frequencies. Okay, frequencies generally we deal with, right? So you see over here, it can this particular op-amp IC741. So if you go with modern day op-amp, so it can withstand 20 megahertz frequency as well. So that's the advantage we get. So, and that's why if you see, that's why op-amp is designed in such a way that not only it provides high input impedance and high gain, on top of that it also provides high bandwidth, okay, or infinite bandwidth ideally, or high bandwidth, that means around 20 megahertz. Okay, so that's the reason that why exactly op-amp is selected for most of the application, especially for amplifying and then performing various applications. Not necessarily that you can only perform amplification, but that's the second reason that why exactly we select op-amp for various application, because it can withstand almost all of the frequencies, okay, from 0 hertz to maybe 20 megahertz. Okay, alright, so what I will do now, I'll just zoom out this particular image. Okay, so you see this is a plot between the gain and a frequency. You see below there is frequency up till 10 megahertz and this is the gain. So if you look over here, so now what I'll do, I'll just click on this V out, and now if you look over here, I'll just move my cursor. So as I'm moving my cursor, just look over here, the frequency and the magnitude changes, right? So you see as I'm moving my cursor, the frequency and the magnitude along with the phase angle also changes, right? So you see at lower frequency, okay, so maybe till this particular frequency, I don't know what the frequency is, maybe up till 63 kilohertz, or maybe if I go a little bit above that, so maybe up till 200 kilohertz, the gain is almost constant till 6 dB. Okay, and you see there isn't any such sudden change in the angle, right? So at low frequencies we are able to achieve 180-degree phase shift, but as we keep on increasing the frequency, though, so the phase angle also changes, right? Phase shift it changes, right? Now if you look over here, as I am moving down, that means, you know, as I am increasing the frequency, maybe if I am dealing with 500 kilohertz, so you see the gain decreases, and with the gain the phase angle also decreases. It was 180 degree earlier, now it is 108 degrees, right? So as I keep on increasing the frequency, so at certain point the gain will decrease, and at the same time the phase angle will be almost equivalent to 0. You see, at this particular point, maybe you know, the gain is almost minus 20 dB, maybe phase angle is also 0, almost 0, not exactly 0 but almost 0, and the frequency is around 6 megahertz. Okay, so you know, we can analyze lots of things with the frequency response. So this is the frequency response, and this one, you see this dotted line, it is the phase response, right? How exactly my phase angle is changing with the frequencies as I'm increasing the frequencies and all. So this is what we can actually see with the help of this particular plot. I believe that you all guys are understood this particular concept in detail way, right? Now let me just go back. So for that, what I will do, I'll just click over here, tile windows, and you see again I moved back. Okay, so whenever you do such kind of things, so you see this entire, you know, thing, it gets changed, right? It changes its position. If you look, if you look over here, it was you know, present below this particular graph, the input output waveform. Now it is now it has moved above, right? And this particular circuit which was present over here, now it moved over here. So what I'll do, let me just move this one over here. So you have this privilege to move this particular entire images and all. Okay, so you can do this as well, as this particular circuit diagram is responsible for frequency response, you see over here, and this particular circuit diagram is responsible to change the, I mean, to see the to analyze the input output waveform, right? Because we had provided sinusoidal waveform, which I had clearly mentioned over here, right? And we had also mentioned the transient analysis over here. So now I would also like to explain you one more thing. So I'll just delete this input waveform, and I'll just delete this output waveform. Now let's suppose if I want to analyze the input output waveform separately. Okay, so what I will do, I'll just click over here on this particular window, and then I'll just click on this add plot pane, and then what I will do, if I want to plot input waveform over here in this particular window, I'll just click over here, and then I'll just click on this input node. You see, I'll get my input waveform. Okay, and now let's suppose if I want to plot my output waveform over here, I'll just click over here, and then I'll just click on the output node. You see, I'm getting output waveform. If I want to change the color, I'm able to do that with this particular colors that are available. I'll take pink color only. I'll click on OK, and if I want to analyze this waveform, so I'll just zoom it out, and you see my input waveform, it fluctuates from 1 volt to minus 1 volt, right? 1 volt to minus 1 volt, and my output waveform, you see, it fluctuates from minus 2 volts to 2 volts, right? And you see the phase angle or phase is almost 180 degree. So there is a 180 degree phase shift between the output and input waveform. On top of that, we are also able to get the amplified form of the input signal. Okay, so this was all about the inverting amplifier and its simulation onto the LTSpice software. I believe that you understood this particular concept in depth. Okay, and at the same time you also understood the frequency response, right? Like why exactly we are plotting the frequency response, why the bandwidth of any op-amp or any system should be as high as possible. Okay, you understood, or you got the answer for this basic questions. Okay, these are the most important things that you should always remember. Okay, great. So I really hope that you understood and you enjoyed this particular session. If you have any sort of doubts anywhere, it's my request to you that you please ask those particular doubts in the communication section. I will surely help you out there. If you enjoyed this session, then make sure to like, share and subscribe to my channel. Thank you.